Okay. This is the second districting video. Okay. So we've solved that min deviation problem. Next up, we're going to start trying to, I guess first we'll start imposing or seeking compact districts that have nice, friendly shapes. So to explain what we're about to do, let me click on this districting models handout. So this is in the districting examples repository. So if you downloaded the code from there, you would have gotten this PDF file as well. So far we've been working with this Oklahoma county level graph, which again, you take by putting a vertex inside each one of the counties, and then you connect those two nodes if the associated counties share a border. So this is the graph that we get for Oklahoma, 77 nodes representing 77 counties in Oklahoma. And I think in the Network X video, we talked about the neighborhood or the adjacent nodes or adjacent counties. So for Payne County, we had seen that there were 5 neighboring counties. Okay. So one of the constraints that we'll impose in this next model is those population balance constraints. So instead of seeking a minimum deviation plan, we're going to put restrictions on what kind of a deviation is permitted, and then we'll try to make the plan as compact as possible. So what we'll do is we'll take the entire population of Oklahoma and divide it by 5, and that will give us the ideal district population, which oftentimes will be fractional. So we may need to allow a little bit of tolerance, a little bit of deviation here. And so what's typical for congressional redistricting is a 1% deviation or smaller. So what this would mean is to say, take whatever that ideal district population is and multiply it by 0.995 and 1.005. And that would give you some bounds for your district populations. So for 2010 for Oklahoma, that would have meant the 746 number and the 754 number. Okay. So the model that we're about to do is the compactness measure that we use is something called cut edges. So to illustrate, suppose that we had a state that had 16 counties and they were all arranged in a grid fashion like this. So I haven't drawn all of the edges here. Some of them are dotted, but so think about just a 4x4 grid. Now there are multiple ways that you could split up these 16 nodes into 4 districts, each with 4 nodes. So one way is to say, basically just take the columns of this grid, and you could call those each a district. Or another way is to take these kind of squares in the corners, kind of the postmarks, kind of the stamps of this state, and that would also be a way to split up the 16 counties into 4 districts, each of which is contiguous. And this would be, intuitively, this should be more compact. I mean, the shapes here are prettier than the kind of the long, skinny shapes over here. And in terms of the graph, if you count how many of these edges are cut between districts, you'll see that there's one edge here that's split between districts, one here, 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 and here. So in total, this compact looking squares plan cuts 8 edges. Whereas this non-compact plan over here with these column districts cuts a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it cuts actually 4 more edges. So this is a I think, a pretty reasonable measure for compactness that's easy, I think, to describe, which is important when you're talking about drawing districting plans for the public and for lawmakers. And if these things are too complicated, people just aren't going to understand it. Okay, so what we're going to do is we're going to try to write an IP model that will partition the nodes of this graph into the appropriate number of districts, which we're using as k. K is the number of districts, such that the population of each of these districts is between those lower and upper bounds L and U. And we also want to minimize those number of edges that are cut between districts. So to model this, we have the exact same x variables as before in the deviation model. And we'll also define a binary variable for each one of the edges on our graph that will just tell us yes or no is one of the edges cut. Okay, so the constraints here probably look pretty familiar. We have these assignment constraints from before. We have the binary restrictions on the variables. We have a similar sort of constraint that we had before, talking about the population of each of these districts. Previously, they should have been between y and z, which were variables. But for this problem that we're studying here, L and U are parameters. So these are fixed numbers that are opposing our 1% deviation. And then we also have a little bit of extra work to, I guess, one, to express that objective, that we're minimizing the number of edges that are cut. And then also, we somehow have to link the x and the y variables, which in this case, y is a binary variable for each edge, indicating whether it's cut. And an edge is cut whenever the two vertices that touch that edge are assigned to different districts. So if you consider an edge that connects vertices u and v, if vertex u is assigned to district j, but the other vertex v is not assigned to district j, that means it must be assigned to some other district. In that case, that edge should be cut. And so in our model, if u is assigned to district j, but v is not, we have 1 here and we have a 0 here, and that will force this y variable to equal 1, which will then represent that we're cutting that edge. Okay, so this is the model that we're going to code up. So let's go to our districting examples file that we had downloaded and unzipped. I'm going to click on starters, and we're actually going to skip D2 and we're going to go to D3, just because we're going to go straight to working with GeoPandas. Okay, so I'll copy in this information to read in the file, our JSON file. Okay, so that's where I've stored that file. Okay, so let's import JerryChain, and then I'll use JerryChain to read in the graph. And then I'm going to for my own sake, I'll go ahead and print each node number, the associated county name, and the population of that county. And like before, I'm also going to assign that county population to this totpop field, which will make it easier to write things later on. So I'll go, oops, and that one. Okay. This doesn't look like a starter, does it? Okay, so let me delete some of this. Okay, so this is probably what our starter should look like. Okay, so first, we're going to be using a 1% deviation, or that's what we would like to use anyway. So let's just go ahead and use a 1% deviation for now. And then we'll calculate what's the total population, which is going to be the sum of all of the node populations. Okay. So our ideal district population is going to be whatever that total population is, divided by k, where k is the number of districts. So I should probably specify that we're working with 5 districts. Okay. And then we need to allow a little wiggle room around that ideal population. So what we'll want to do is, like what we had in here, let me see if I can find it. Okay. So we want to take this ideal district population and then multiply it by some factor. It's going to be 1 minus a little bit of something, basically 1 minus half of the deviation. So we want to do 1 minus deviation over 2, and we'll multiply that by that ideal population. And we'll do the same thing for the maximum allowable district population, but we'll have a plus. And then just for our own sake, let's go ahead and print that we're using L equals this value and U equals this value and K equals, in our case, 5. Okay. If we do that, we'll get something like this. And it's not possible to have a fractional population like this in our districts. So we can actually, I guess in terms of this lower population, we can round this up to an integer. And so if you're familiar with math functions, this round up operation is called the ceiling of a number. So we want to do the ceiling of this thing. And in order to use this function, we actually have to import the ceil function, or we import this package in Python called math. So we'll do math.ceil. And I guess before that, I'll need to import math. Okay. And then likewise, this maximum permissible district population is fractional, and it doesn't really make sense for us to say you can't have any more than this whole number plus 0.95 people. So we can just go ahead and round this one down, which the math function for that is going to be floor. So now we get integer lower and upper population bounds. Okay, so this will ensure an overall 1% deviation. And I guess more specifically, this is a plus or minus a 0.5% deviation. Okay. So once we've kind of defined those parameters, we can start building our model. I'll do that. Also create the variables. So we have the binary assignment variables from before. So g.nodes, k, and then this will be a binary variable. Each one of them will be binary. So recall that this xij variable is 1 if county I is assigned to district j. And then in this cut edges model, we also have binary variables for each edge. So here I will say I'm adding a variable for each edge. And these variables should also be binary. So this variable, maybe I'll use UV. Variable YUV equals 1 when edge UV is cut. So this is the edge between vertices U and V. Okay, run that. Everything seems to be working. Okay, so now I'll set my objective. So set objective. We will minimize the number of cut edges, minimize the number of county pairs that are split into different districts. And so here I want to put the sum of the y variables. So I could do this like this. So I could say YUV for all edges UV. There's also a quicker way I could do this. I could just say quick sum y. These will actually end up being equivalent for Gurobi. So Gurobi gives you this kind of shorthand notation. If you just sum over all of the y's, you could write it like this. But a little more explicit, I'll write it like this. Okay, let me run that cell. Okay, everything's working so far. So if I go back to that model, one of the easy constraints, one that we've already done, are these assignment constraints. So let me do those. I'm adding constraints, so that's why I've got an S here. And I want to add a constraint for every node. And the constraint is going to say that node or that county should be assigned to exactly one district. So I want to do summing over all xij's for all districts j. I should also add those population balance constraints. So I want to add constraints saying that each district population at least L and at most U. So if I wanted to, I could probably just copy that over from our last one. But the only difference being that you need to change the y variable and that z variable to L and U, because our most and least allowable district populations are now fixed quantities. L and U. Okay. And then, okay, so now we've got the objective, we have the assignment constraints, we have the population balance constraints, and then we have the binary restrictions. So all that remains are these constraints that link the assignment variables X and the cut edge variables Y. Okay. So these are going to be a whole bunch of constraints. So again, I'll use S here. And they say that, well, the way the comment is written here is that this edge ij is cut if I is assigned to a district V, but J is not. Maybe I'll change this up. Let's do edge UV is cut if U is assigned to district J, but V is not. Okay. So this will say if U is assigned to J, but is not assigned to J, then that edge between them, UV, is cut. So this constraint we want to add for every edge UV, and also for every district J. So I got that right. And then I'm also going to do m.update just so it doesn't print a whole bunch of things when I write out these constraints. I think otherwise, if I don't do this, it's going to print something for each one of these constraints. And so that's going to be for each edge UV and for each district J. So there's something like 200 edges and 5 districts. So there'd be something like 1,000 different things that would print here. So to avoid that, I just go ahead and write m.update. Okay, added those constraints pretty quickly. Now let's solve. And it doesn't like it. It says model is infeasible. I wonder why. Okay, so let's go back up to population bounds. So the population of every district, we're imposing that it be between this number and this number. But if you'll recall, Oklahoma County had a pretty large population. So let's see if we can find Oklahoma County. Oklahoma County has a population of 796,292. 796,292. So 796,292 is bigger than what we allow in a district. So it's actually not possible with the new 2020 census data to draw a districting plan for Oklahoma that keeps all of these counties intact and that satisfies that plus or minus 0.5% deviation. So I'd say for your projects, I would keep this deviation like it's written here, but just for illustration purposes right now, I'm going to change this to a 2% deviation. A plus or minus 1% deviation. So now that I've changed this deviation, I've permitted a larger deviation. I need to kind of rerun all of these cells. I need to redefine L and U, and you'll see now with a 2% deviation, U is closer to 800,000. So now it's more than the population of Oklahoma County. And I'm also going to have to kind of recreate this model because some of these constraints down here were written in terms of those old L and U values. So I need to kind of create a new model object, create these variables all over again, and add the constraints and objective and whatnot all over again. So let me rerun all of these cells. And this may take a little while. This is a somewhat challenging optimization model. I'm just going to let it run. It seems like it's making decent progress. So if you look at these two columns right here, these are reporting the upper bound, which, or I guess it's reporting the best feasible solution that we found so far. And this column right here is representing the best bound that we've been able to argue for. So, okay, we're done now, but this last line right here, Gurobi knew that this optimal objective value was somewhere between 34.7 and 37. And I guess because our objective had all binary variables, any feasible solution should have an integer objective value. So actually, if we wanted to, we could round that up to 35. We would know the objective was somewhere between 35 and 37. But anyway, Gurobi was able to keep going. So it actually did more steps than what it showed here, but it kept going. Ended up visiting 46,000 branch and bound nodes. And this last one that it printed was at 44,000 branch and bound nodes. So it still visited another, what is that, 2,000 or 2,500 branch and bound nodes after it printed this last line. So it's pretty quick. So in total, it took about a minute, and it says that 37 is the minimum number of cut edges between districts with this 2% deviation. Okay. So let's retrieve the districts just like we did before. So maybe I can just copy paste this. Okay, so it'll give us the districts in terms of the nodes. It'll give us the districts in terms of the county names, and also the district populations. And then maybe I'll go ahead and print those too. Okay. So we have our 5 districts again. One of them is just Oklahoma County. One of them is Tulsa County and Comanche County. If you know anything about Oklahoma and counties in Oklahoma, this doesn't make a whole lot of sense as a district. So Comanche County is where Lawton is located. So it's not adjacent to Tulsa. So this district should be not connected. I guess if we wanted to see that in terms of the graph, I could run this code. Let me do that. If each of these districts are connected or not. So the first district is connected, the second district is connected, and the one with Comanche County and Tulsa County is not connected. And then also this District 3, which is the 4th in the list, is also not connected. Okay, but if we wanted to visualize this, we can. So let's see. We're going to need to work with GeoPandas again. So just 1 second. Okay. So as I mentioned, we need GeoPandas. So let's import GeoPandas as GPT. So this is what we'll need for working with shapefiles and drawing maps. So this might take a second to import. Okay. And now I need to find that OK County shapefile, which is actually stored in the same folder as my JSON file. So I'm just going to copy this file path, bring that down here. Okay, so this should be in that districting data 2020 county zip file that was on Canvas that you downloaded and unzipped. And then we will read that data frame from that OK County shapefile. So I'll do that like this. Okay, so it read that pretty quickly. Now, so somehow we need to add a new field to this data frame showing for each county which district it's assigned to. So give me 1 second. Okay. We're going to define something called assignment, and this will just tell us for each one of these counties which district is it assigned to. So initially, we'll just say that every county is assigned to this made-up district called number 1. And then we're going to figure out which district each one of them is assigned to. Okay, so this assignment, this variable right here, this list is ultimately what's going to be corresponding to the data frame, the GeoPandas data frame. And this labeling is going to be something else. This is actually going to be a Python dictionary that we defined in terms of the kind of our optimal solution X star. So node I will get mapped to district J if that xij variable is taking a value of 1, but because this is floating point, we're just going to say if it's at least 0.5. And we actually need to write this out for every I and for every j. So I need to say I maps to j for all I in g dot nodes and for all j in range k if that holds. Okay, so let's see. So if you recall, each one of these counties or any geographic unit in the census hierarchy has a GeoID. And so we're going to define a map that will tell us, basically, if you pass this map a GeoID, it'll tell you what node in the graph it corresponds to. So node with this GeoID. I'm going to say some GeoID gets mapped to node I, or I in g.nodes. So now the question is, what GeoID gets mapped to node I? Well, that's just g.nodes I GeoID 20. I know there's a lot of setup here, but this will make sense in just a second. Okay. So now we're going to iterate over the data frame, every row in the data frame. So pick a position u in the data frame, or u in so u, the values that u is going to take are 0, 1, 2, 3, and so on, all the way up until, in our case, 76. And these are going to be like the rows of our data frame. And so first we're going to figure out what's the GeoID for that particular row of our data frame. So that's going to be the data frame look for that GeoID 20 field, and then we ask in row U, what's the GeoID stored there? And then we ask what node in G has this GeoID. So that'll be, we'll call it I, but it's going to be node with this GeoID. Okay, so now we have a row in our data frame. We have the GeoID associated with that county that's in that row. And then now we know in the graph, what's the node number. So now, with this labeling dictionary, we know what district node I is assigned to. So the district that it's assigned to is labeling I. So whatever that district number is, if it's district 2, let's say, we need to assign that to this field in our data frame. So first we'll temporarily store it in this assignment list. Okay. So this position U in our data frame should be given the same number that I has, that node I or county I has. Okay. So now that we've got this assignment list that will just tell us for each row in this data frame what's the corresponding district number, now we can just add this as a field to our data frame. Okay, so to add it to our data frame, we'll just create this new field, this new column, and we'll just plug in directly assignment. Okay, so now it's in our data frame. We've added a new column to our data frame, and then now we can draw. So I'm going to create a figure. I'll call it myfig, and I'll do dataframe.plot. I'm going to draw based off of what's in this column called assignment. And then after I plot it, I'll just get that figure. So I think if I run this, it should go ahead and draw our map. Okay. So there's our map. So like we had said before, one of those districts was Tulsa County and Comanche County, which are not connected. But for whatever reason in this districting plan where we're trying to minimize the number of cut edges, that ended up being part of an optimal solution. So it's not contiguous. But at least if you look at some of these districts, like this purple district, this yellow district, and to some extent this green district, they look reasonably compact in shape. I mean, you don't have crazy jagged edges going between these districts. It's not too bad. But of course, it's not connected right here. Okay. So that does it for this min cut type districting plan, so far without contiguity constraints. So actually contiguity constraints are what we're going to deal with in the next episode or lecture.